So in today's lesson, we're going to prove the product rule. But let's actually go back to first principles, the basic first principles, what it is. So if you have a function and you want to find the slope, so recap that the slope is rise over run, right? And we can describe this as y to the change in the y and the change in the x. Or if we were to move to function notation, it would look like this. This is still x2 over x1, same idea as this. But then we're going to actually use this in a different way. So instead of calling it x2 and x1, we'll call it x plus h minus f of x over h. So basically, h is the gap between the first point and the second point. And we want the gap between these 2 points to be very, very close to each other, such that you want the h to be close to 0. So what does that look like in terms of using limit notation? So first principles is the limit of the following, of the slope, okay, over here. And this is the same thing as f prime, or we can call it y prime, or dy dx, or I rock. So if I were to write the following, using the same notation, but using a different function, right, this would be the same thing as g prime. So in our past lesson, we proved using first principles power rule. So power rule is the following. If we have a function that can be expressed in this format, the derivative is n. You bring the power down as its coefficient, and then you drop the degree by 1. For example, if you have x to the power of 3, the derivative is 3x to the power of 2. The degree drops, but the 3 is brought down in front of the coefficient. Also in the last lesson, we actually can combine different functions together. So what I mean by that, if you have a function such as f of x plus g of x, all right, that is the same thing. To find the derivative, you have f prime x plus g prime x. So if I give you an example, you have x squared plus x3. If you want to find the derivative of this cubic, you do the same thing. You use power rule for in the individual pieces. So if y is equals to f plus g and the derivative is f prime plus g prime, if we were to move to a product, if the function is a product of two functions, would the derivative be f prime g prime? That is the question. And we can actually put this to the test. For example, let's let f of x equals to x squared times x. So let's let these two functions be the two functions being multiplied parabola in a straight line. If you want to find the derivative using this method, I'm not saying it's right or wrong yet, let's actually see whether it's true or not. So if you take this, the derivative of this using power rule is 2x, the derivative of this, or the slope of this, a linear function, is 1, and we end up getting 2x. However, if we were to multiply the product of these two functions, which is x3, to find the derivative, we get 3x squared. Notice how these two answers are not the same. Well, in this case, this is the proper answer because this is making an assumption based on what we thought about the sum. So in this case, this method is not true. In other words, fg prime is not the same thing as f prime g prime. So the question is, what is it? So in the next slide, we're going to actually prove it. So recapping first principles, if y is equals to f of x, you want to find y prime, or dy dx. You take the limit as the gap between the 2 points gets closer to each other. So that is what first principles looks like, okay? But what happens if instead of having f of x, I have the product? How would the derivative change in terms of limit notation? It would look exactly the same thing, but instead of having f by itself, we have f of x plus h, and we have a g. There is a product in the numerator of the limit notation. So we have this over h. But the question is, what can we do? We cannot substitute the 0 in there because if we did, we end up getting a 0 over 0. All right, if we subbed in h into here, these two, we end up getting 0 over 0, which is indeterminate, which means that there has to be something else we can do. So I'm going to show you in the next step. So continuing on from our previous slide, if you notice here, this is a similar statement as previous slide. We have the product of something, and now we're going to use the first principles using this product function. And I'm going to just reveal each step as I move the green box down. So if you look at this first step, there's nothing really much I can do here. We cannot expand. F and G are not variables, they are functions. There's nothing we can factor out. There's nothing common between the first part and the second part. So we're going to use a technique that we have seen maybe 2 years ago when we did something called completing the squares. I'm going to show you the next step, which is this one here. So if you notice the red, we're going to insert something into the system, into the numerator, but we're going to have to balance it off because it doesn't really belong there. So if you look at these terms, they're exactly the same, but one's a negative, one's a positive. So this technique you may have seen when you did completing the squares. So I'm going to put it on top of here just to recap completing the squares. So this is standard form. And back in the past, to change from standard form to vertex form, which will tell us the turning point of the parabola, you're going to have to do something called completing the squares. Not to get into too details, but to complete the squares, you had to insert something into the system, but balance it off with the same constant. And what is that constant going to be? In our case, it's going to be 1. And after that, now we can actually factor the first 3 terms using perfect squares, and then we have -1. So the idea of inserting something into the system and taking it out means we have more things we can do, more different techniques we can apply. So for example, standard form, we did something, adding something into the system, subtracting it, and we did factoring, and we ended up with vertex form, which tells me another aspect about the parabola. So in our case here, all right, we're going to insert the red, all right, and what we can do is, if you notice between the first 2 terms, there is something in common. So over here, so look at the first 2 parts here, the blue and the red. Okay, so notice how we can do something with the first 2 terms. So notice how this one has a gx plus h and a gx plus h, and look at the last 2 terms, it has a fx and fx. So what I'm going to do next is I'm going to put this up here. All right, I'm just going to write this out as clearly as I can, and I'm going to split them up. Okay, when I split them up, I want to actually split the fraction up. So I'll do my best to write as clearly as possible. Over h, that's the first fraction, and then we're going to just decompose, meaning we're going to split the fraction up. Okay, so that's the next step. All right, sorry for the mess, it's going to get really tight over here. So this is what we have. There should be big brackets around here. Okay, then what's next? Well, if you look at the first group there, you can actually common factor this out. So notice how this part here, the numerator, we both have a gx plus h and gx plus h. So what we're going to do next is we're going to factor this out. Same thing for this one here. If you have a look at the second fraction, it has a fx. We're going to factor this out, and that's going to move to the next step, which I'm going to reveal. Let me just take the thing and reveal it right over here. Okay, so that's what we did here. So as you can see here, this one is factored out. We have this left over. We factor out the f of x, the red part, it's factored out. And the next thing is we're going to actually take this and split this up. All right. No, we're going to rearrange this. So this is just a slight rearrangement. Basically, we just took the g of x plus h and just move it to the right-hand side. Sort of like saying 2 times 3 is the same thing as 3 times 2. We're just going to just reorder it a little bit. Okay. And after that, what we're going to do next is the following. So the next step is to use the properties of limits. So if you notice about this function here, we have a limit of this huge expression. And if you notice, this is actually, imagine a plus b, okay? So there was a property limit where you can actually split the function into 2 parts. So over here, we have a first limit of the first part of the function, and then of the expression, and then the second part. So we're just splitting it using the following limit notation. So I'm just going to show you that limit that we did in the past. So if you have, for example, f plus g is the same thing as limit f plus the limit g. So we're splitting up into 2 limits. So the last step is taking this expression over here and using another limit property where we can split it again into 2 products. So if you look at the first group here, we have a fraction and then we have multiplication. Over here we have a fraction or rational expression, and then we expression, and we have a function. So there's a product. So we're going to split this up into another limit notation. So I want to split this up into the following. So limit h f of x plus h minus f of x over h. So that's the first part. This one here, I'm going to put a limit, and they're next to each other because it's a product, gx plus h. And then the third one is this one here. So I'm going to write down limit h0 f of x, and then another limit and then h, and then this, and then we have the rational expression, and this is where we stop. So there's 4 parts to this. And the question is, Miss, can I sub in 0 for h? And the answer is not really. So let's actually look at the first part here. So the first part looks like something we've seen before in the very first 2 slides. This here is the first principles. This tells us the derivative of what function? Of the f function. So this whole expression here becomes f prime. Okay. The next step is the following. Can we sub in h for 0 into here? Yes. And when we sub this in, we end up getting g of just gx. Remember when we sub in the h for 0, the limit is gone, so we end up with gx. Okay. The next step, plus. This step here, the question is, can we sub an h into this? And the answer is no. And because h has no effect on f of x, that means your outcome is going to be f of x. Because f of x is not affected by h, so we end up getting just f of x. And the last part is this part here. This looks familiar. The very first slide that we see. This actually looks very similar to this. This actually is first principles, which tells us the derivative of what function? The g function. All right? So what's happening right now is this expression that we have here is the product rule derivative. And let me reveal the bottom part here, over here, which is exactly the same thing as what I wrote down here. So let's do an example where we can apply the product rule. So whenever you see a function that's being multiplied together, you're pretty much going to be using product rule. So let's recap product rule. So f, g, so I'm just going to write a different way. So what this means here, this notation means if you had a function that's being multiplied together, 2 functions, and this little dash means prime, the derivative is going to be the following. It's going to be f prime g plus g prime f. Now sometimes for me, I like to write L and R. Right? L and R is the same thing as their functions. It's just L means to me the left function versus the right function. Okay? So in this case, for me, this would be the L, this would be the R, left and right. And if I were to write the derivative, it'd be exactly the same thing as above, but you take L prime and then multiply by the original R function, plus then R prime's next, and then multiply by L. So it's up to you what you want to use. So over here, let's find the derivative. So there's actually a couple of choices you can do. You can, if you wanted to. If you don't want to use product rule, you can expand, and then you end up getting a cubic, and then you can use the power rule. But let's actually use the product rule. So in this case, this is going to be my left function. Oops, my left function. This is my right function. And I want to find the derivative of this. Okay, so I'm going to move it down here. So f prime. All right, and in my case, it's going to be L prime R plus R prime L. I'm just writing down the product rule. The next thing is, if you wanted to, I'm just going to substitute what my right and my left function is. I'm going to keep the dashed here, So what's my left function? It's the parabola, x squared minus 2x plus 1. My right function is the linear. What's my right function here is 2x minus 3. My left function here is going to be my parabola, okay? But notice how I haven't really done the derivative of each section. I just did the product rule. The product rule is finished. Now we have to execute each bracket, okay? So over here in black here, what does this mean here? This means find the derivative of what's inside the bracket. So you use power rule, which is 2x minus 2. So that step 1 is done. This one here, we don't have to take the derivative. There is no prime here. So we just write down again. Now this one here, for the next one here, oh, there's a prime. So that's a prime. So prime doesn't mean to the power of 1, it means prime. So let's find the derivative of this. What's the slope of this? It's going to be 2, so that's 2. And then this one here, there's no prime. We just write down the following, and you are done. You are not required to simplify this. What I mean by this, don't expand and collect terms. Leave your answer like this for now. We will need to combine like terms if there's more next steps, but that'll be in the next unit.